Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 4, Contextual Applications of Differentiation, and today we're doing the Chapter 4 review. Enjoy today's notes. All right, everybody, welcome to the Chapter 4 review on our chapter on contextual applications of differentiation. Again, a reminder that reviews do not cover all of the material from lessons, but should remind you of key points. In order to be prepared, you should review all of your packets from Unit 4, all of the notes, all of the practice problems that we've done. That is the way to make sure that you are best ready for the Chapter 4 test. Let's get into it. Number 1, the figure shows the velocity v is equal to the derivative of the position is equal to f of t of a body moving along a coordinate line in meters per second. So this looks like a example of a rectilinear problem or a particle motion problem, and they told us here that the graph that they gave us or the figure that they gave us is the velocity. So given that, I'm just going to emphasize that so that we keep that in mind as we're looking at our questions. A, when does the body reverse direction? All right, so we know that velocity is speed with direction. Specifically, when the velocity is positive, when it's above this t-axis, we know it's moving in the positive direction. And when the velocity is negative, below the t-axis, we know that it is moving in the negative direction. So I noticed that at t equals 4, it went from moving in the positive direction to moving in the negative direction. So at t equals 4, this object turned around. Similarly, at 8, it was moving in the negative direction and then suddenly started moving in the positive direction. So at both t equals 4 and t equals 8, and I'll just say the reason is since the sign of v of t changed at each of those points. So we know that the body reversed directions. It changed which direction it was going. When is the body moving at a constant speed? Remember again that speed is the absolute value of velocity. And so I'm looking for really any places where the velocity is constant here. And so really I'm seeing that this is, it's a linear function. This is more of a linear piece. Here I see a constant, right? It's not changing from t equals 6 to t equals 7. It is staying at that velocity of negative 3 or a speed of positive 3. So I would say between, or so on, the interval from 6 to 7. So on 6 to 7, it is moving at a constant speed. What is the body's maximum speed? Again, speed is the absolute value of velocity. Looks like at this point up here it has a velocity of 3, and then down here it has a velocity of negative 3, so the speed is 3 as well. This problem does not ask when that occurs. It asks what the maximum speed is, so that is going to be 3 units per second, meters per second in this problem. So meters per second for this. And if we needed to say when that was, that occurs at t equals 2 and on the interval from 6 to 7. At what time intervals is the body slowing down? So where is this slowing down? That would be, remember we said that in order for an object to be slowing down, that the velocity and acceleration must have opposite signs. Because we said that if an object is speeding up, that the velocity and acceleration have to have the same signs. So here, on this interval here, we notice that the slope of this is positive. That's the acceleration. And so this is a case where this object is speeding up. So I'm going to put speeding up on this. Here, from here to here, we see that the object has a positive velocity but a negative slope or a negative acceleration. So this is slowing down on this interval. And then from here to here, negative velocity, negative acceleration, because the slope is negative, so it is speeding up on that interval. This is neither, because the slope of the acceleration is 0, so it's not going to have opposite signs. And then here we have a negative velocity but a positive acceleration, since the slope here is positive, so it is slowing down here on that part. And then we are speeding up on this part here because it is a positive velocity with the slope being positive or the acceleration being positive. So where is this slowing down? I'm looking really at this interval from here to here and this interval from here to here. So what are those times? This looks like this is going to be on 2, 4, and so union 7, 8 would be where that object is slowing down because the velocity and acceleration have opposite signs. Again, reminder that to find the acceleration of a velocity function, we're looking at the slope of the line on those intervals. And so since this slope is positive, the acceleration is positive here. Since the slope is negative, the acceleration is negative here. Cool. Number 2, L'Hopital's rule. Again, from this most recent section 4.7, we know that L'Hopital's rule only applies in functions or limits that are in indeterminate form. So let's do direct substitution and check first. If we do 2 minus 2 over 2 squared minus 7 times 2 plus 10, that's going to be, 0 over 0, which is, in fact, that indeterminate form. Again, if we're looking at like AP exam quality work for this, we would want to make sure that that side work is not being shown as equal to that original limit. But we want to say that the limit of the numerator, so the limit of x minus 2 as x approaches 2 is 0, and the limit of the denominator as x approaches 2 is also 0. So L'Hopital's rule applies. And then we're going to apply it. We're going to use it. So if we do that, we get that this original limit up here is going to be equal to the limit as x approaches 2 of the derivative of the numerator, which is just 1, divided by the derivative of the denominator, which is 2x minus 7. And then we're going to do direct substitution again. So we're going to plug in that 2. That is 1 over 2 times 2 minus 7, which is 1 over 4 minus 7, or negative 3. So our answer here is negative 1/3 for our limit for problem number 2. Nice. Number 3, let's try this one out. Let's try that direct substitution first. Let's see what happens. So if we do that in this one, we get 3 times 0 squared divided by e to the 0 minus 1 minus 0. So that is 0 divided by 1 minus 1, or 0 over 0, which again is indeterminate form. So that's our side work. We're going to show that these two limit expressions equal 0. So the limit of the numerator equals 0, and the limit of the denominator is equal to 0. So L'Hopital's rule applies. And we're going to say that this is equal to, let's see, the limit as x approaches 0 of the derivative of 3x squared, that's 6x, divided by the derivative of e to the x, which is e to the x. The derivative of negative 1 is 0, so that goes away. And then the derivative of negative x is negative 1. So if we do direct substitution again, we have 6 times 0 divided by e to the 0 minus 1. That's 0 over 0, or indeterminate form again. We would once again want to show that the limit of the numerator and the limit of the denominator are equal to 0. So let's quickly do that. The limit as x approaches 0 of 6x equals 0, and the limit as x approaches 0 of e to the x minus 1 equals 0. So L'Hopital's rule applies. And let's do this one more time. What's this going to be equal to? Well, this is going to be equal to the limit as x approaches 0 of the derivative of 6x. Hey, that's 6. And that's, again, nice because now there's no x in that numerator, which means I can't get a 0 in that numerator, which means I can't get indeterminate form. But the derivative of e to the x is e to the x, and the derivative of negative 1 is 0. So this is just 6 over e to the x, which is going to be if we take that limit, 6 over e to the 0, or 6 over 1, which is 6 for problem number 3. So one where we need to do L'Hopital's rule twice in order to do this. Number 4, hey, the instructions here say use L'Hopital's rule when possible. This is not a limit problem, it's just a derivative problem, so we need to use the quotient rule in order to do this one. Really, in this chapter, we're just trying to hammer that these are not the same, right? They're different, and we need to make sure that we know both rules separately for this. So what is this derivative equal to? If we take the derivative of that, this is going to be the derivative, is going to be low, so 5x plus 1 times d high, so the derivative of 3x minus 2 is 3, minus high, 3x minus 2 times d low, the derivative of the denominator is 5, all over low squared, so 5x plus 1 quantity squared. If we wanted to, we could simplify. So this looks like what? 15, if we distribute, and we distribute 15x plus 3 minus 15x plus 10, all divided by that 5x plus 1 quantity squared. So that those look like they cancel, and I have what? 13 over 5x plus 1 quantity squared would be the derivative for this particular problem. Nice. So don't confuse L'Hopital's rule with just the regular quotient rule. One is only for limits that are in indeterminate form, and the other is when we're just taking the derivative of two functions that are being divided. Nice. If the length L of a rectangle is decreasing at a rate of 2 inches per minute, while its width is increasing at a rate of 2 inches per minute, which of the following must be true about the area A of the rectangle? So we're dealing with a rectangle. Let's draw it. We've got a width, we've got a length. What do they tell us? That the length is decreasing at a rate of 2 inches per minute. So the length is changing. So dl dt, it's decreasing. So it's a negative 2 inches per minute. And the width is increasing. So the change in the width over time is going to be increasing at a rate of 2 inches per minute. So positive 2 inches per minute. Which of the following must be true about the area? So the area of a rectangle we know is length times width. And we can take the derivative of this with respect to time because we're talking about what's true about the area itself. So we don't know that the area is always increasing, right? It can't be always increasing since we see that the length is decreasing. So there's no way to say that for sure. And they're asking which of these must be true. And we don't know whether it's always decreasing because we have this width that's increasing as well. So these, I would say, would be tough to say right off the bat. How would we determine this? Well, I'm going to take the derivative of this, and let's see what happens. So if we take the derivative, we see that the derivative of the area with respect to time is equal to, well, here it looks like we need to apply the product rule in order to do this. That's going to be the derivative of the length with respect to time times w plus length times the derivative of the width with respect to time. And we know dl dt and dw dt over here. So I'm going to substitute those in. This is equal to negative 2 times w plus the length times 2, or that's going to be equal to 2 times the length minus the width. So the rate of change of the area with respect to time is going to be equal to 2 times the length minus the width. So how do we know whether it's increasing? Well, it's not always increasing, right? It depends on the L and the W. It's not always decreasing because it depends on the L and the W. Is it increasing when L is greater than W? Well, if L is bigger than W, then this is going to be positive, which means that this whole expression is positive. So that rate of change is positive, and therefore it is increasing. So I would say C seems like a good answer here. It cannot be increasing when L is greater than W, because if this was if L was less than W, if this was less than our w, then this would be a negative number, which would mean it's decreasing. So that cannot be our answer, D. And it can't remain constant because it depends on what L and W are. So seems like C is the best answer for this one. Really taking that derivative, factoring out, you can see it depends on what L and W are. And obviously this is positive when L is greater than W. Cool. All right, the following problems are calculator active. So you're allowed to use your calculators on each of these. And actually, I encourage you to use your calculators on these. Key reminders always on calculator active problems is that you are rounding your answers to 3 digits after the decimal place. That is the standard for the AP exam. All right. Brust is riding his bicycle north away from an intersection at a rate of 15 miles per hour. So here is our intersection. I'll call that I. We've got a person, Brust, who's riding northbound. And again, also useful to make sure that you know or have your directions handy. That's north, south, east, and west. And so this is Brust riding his bicycle northbound away from the intersection. Sully is driving his car towards the intersection from the west. So going towards the west, from the west rather, that's Sully. And Brust is 0.4 and Sully is 1 mile from the intersection. What rate is the distance between the two of them increasing or decreasing? So I'm going to draw sort of the hypotenuse here. Generally, intersections on a grid are at right angles. So we conveniently have a right triangle here. As usual for these, I would label my horizontal distance X, my vertical distance Y, and just to continue with those variables, I'll call the hypotenuse in this problem Z. Let's talk about what they gave us. So Brust is riding his bicycle north away from an intersection at a rate of 15 miles per hour. Rate of 15 miles per hour. So this is Brust. He's moving away from that intersection, which means that that Y value is increasing. So dy dt is going to be equal to 15 miles per hour. Positive 15 miles per hour. Nice. We've got that. Sully's driving his car towards the intersection from the west at a rate of 30 miles per hour. So here, as Sully gets closer to the intersection, notice that that x value is going to get smaller. X should be, dx dt should be negative because this distance is getting smaller as Sully drives towards that intersection. So the change in x with respect to time is going to equal negative 30 miles per hour. You need to know the context of this to figure out whether these values are positive or negative. Notice there's nothing here that explicitly says that this is a negative 30 miles per hour. You need to have drawn your figure and to see that that x is decreasing, so therefore dx dt has to be negative. Brust is 0.4 miles from the intersection, so that is y is equal to 0.4, and Sully's 1 mile from the intersection, so that's going to be 1, and these are both miles that we're talking about. What is the rate? At what rate is the distance between the two of them increasing or decreasing? So we're trying to find dz dt, right? They want to know the rate, the distance between the two of them is increasing or decreasing. That's the goal for this. So what have we done? We made our figure. We've listed our knowns and our unknowns. Third step in these types of problems, these related rates problems, is we're trying to find an equation. We need to think of an equation that relates all of these variables together. Since it's a right triangle, I know that my Pythagorean theorem is going to apply here. So I know that x squared plus y squared is equal to z squared. And we're going to take the derivative of this with respect to time. Since our variables don't match, we're going to do some implicit differentiation here. And the derivative of that is going to be 2x times dx dt plus 2y times dy dt. And I'll put these in parentheses. And that's equal to 2z times dz dt. We can substitute what we know in. We are trying to find dz dt. We're trying to get this. So I want to make sure that before I substitute, I've got all of the missing pieces. Do I have x? Yes. Do I have dx dt? Yes. Do I have y? Yes. Do I have dy dt? Yes. Do I have z? No. No, I do not. So I need to do some side work to find this before we start substituting in. Remember, if they don't give you one of the lengths, generally you can go back to the original equation that you had in order to find it. And so I'm going to just do that over here on the side. Using that Pythagorean theorem that x squared plus y squared is equal to z squared, we can see that 1 squared plus 0.4 squared is equal to whatever z is squared. And that's going to be, 1.16 on the left side is equal to z squared. So if we take the square root, z is going to be equal to whatever the square root of 1.16 is. I'm going to leave that there. So that's z. Now let's substitute in what we know. So we've got 2 times our x, which is 1, times dx dt, which is negative 30, plus 2 times our y, which is 0.4, times dy dt, which is 15. It's equal to 2 times z, which I'll leave as the square root of 1.16, times whatever dz dt is. So if we simplify, this looks like this is going to be what? Negative 60. 2 times 0.4 times 15, that's going to give us 12. And that's equal to 2 times the square root of 1.16 times dz dt. And so what's that? That's going to be negative 48 is equal to 2 square root of 1.16 dz dt, which means that if we divide, that dz dt is equal to negative 48 divided by 2 times the square root of 1.16. Luckily, again, this is a calculator active problem, right? We're not trying to do this by hand. But if we plug that into our calculator here, we're going to see that this is equal to negative 22.283 miles per hour. And again, I rounded to 3 digits after the decimal place for this particular problem. Negative 22.283 miles per hour. What does that mean? Well, the fact that it's negative tells me that this distance z is getting smaller. So as this person is going towards the intersection, as this person is going away from this intersection, they're actually getting closer together, the direct distance from Sully to Brust. And so that is why this is a negative velocity for that one. Nice. All right, so for problem number 7, it says the side of a cube is increasing at a constant rate of 0.2 centimeters per second. So let's start with our picture. We've got a cube, which we know has 6 sides, all with the same side lengths, which I'll call x. And we know that the side length is increasing at a rate of 0.2 centimeters per second. So as time changes, the side length is increasing by 0.2 centimeters per second. In terms of the surface area, so this one's a little bit worded a little bit differently, but in terms of the surface area S, what is the rate of change of the volume of the cube in centimeters per second? So we're talking about the rate of change of the volume of the cube. So let's start with our volume equation. We have that the volume is equal to the side length x cubed. If we take the derivative of both sides with respect to time, we get that dv dt is equal to 3x squared times dx dt. Now we know what dx dt is. We already found that, or they gave that to us. That was one of our givens. But we don't know the side length. However, they asked us to stay here in terms of the surface area S. So we don't want this in terms of the side length x. They want it in terms of the surface area S. So I'm going to essentially do some side work over here. And I'm going to deal with the equation for surface area. Now the surface area of a cube, since each side length, or rather each surface of the cube is a square, and there are 6 sides, the equation for surface area is 6x squared. Now, again, they simply said they want this in terms of the surface area S. So what I'm going to do is I'm going to actually try to get this x here by itself. And so I'm going to divide both sides by x. So S over 6 is equal to x squared. And then if we take the square root of both sides, we get that x is equal to the square root of s divided by 6. Don't confuse that with a 5. Looks pretty close to a 5, but it's the side length, or rather it's the surface area divided by 6. Now what I'm going to do is I'm going to take this equation, x is equal to the square root of s over 6, and I'm going to substitute that in for x in this equation here. That's going to allow me to get the change in volume with respect to time in terms of the surface area, in terms of this S, instead of in terms of the side length. So let's substitute in what we know. We have dv dt, change in volume with respect to time, is equal to 3 times, we said x is equal to the square root of s over 6, and that's quantity squared. And we know that dx dt, as they gave us, is 0.2. So I'm going to substitute that in as well. Now, conveniently for us, the way that this is set up, our square root and our squared are going to cancel each other out. And so this is going to be then equal to 3 times s over 6 times 0.2. 3 times 0.2 divided by 6 is going to give us 0.1 times whatever the s is. So dv dt is going to be equal to 0.1s, which means that A is our answer. Great. Number 8. The function f of x is equal to 1 minus sine of x quantity squared, and it's concave up at x is equal to pi over 6. What is the estimate of f of 0.5 using the local linear approximation for f at x equals pi over 6? Local linear approximation, if we're doing that, should be the equation of a tangent line. And so for our tangent line, we're going to need a point and a slope. The point is going to be whenever we plug that x value into this equation. So that is going to be f of pi over 6, which is 1 minus sine of pi over 6, quantity squared. Sine of pi over 6 is 1/2. So that is going to be 1 minus 1/2 quantity squared, or 1/2 squared, which is 1/4. So the point that we have is pi over 6 comma 1 over 4. That's the point for this. The slope we know is going to come from the derivative, because they didn't give us the slope here, but we know that the derivative is the slope of the tangent line. So f prime of x, the derivative of f, is going to be, by the chain rule, 2 times 1 minus sine of x times the derivative of 1 minus sine of x, which is negative cosine of x. And I'm curious what that slope is at pi over 6. So f prime of pi over 6 is going to be 2 times 1 minus sine of pi over 6 times negative cosine of pi over 6. This is where our unit circle knowledge comes in handy. Pi over 6 is 1/2, so that's 2 times 1 minus 1/2 times negative cosine of pi over 6, so that's negative square root of 3 over 2. And then we've got 2 times 1/2 times negative square root of 3 over 2. That looks like that's going to be negative root 3 over 2 for the slope. So what's the equation? So our equation, moving down into this B part, the equation of that tangent line is going to be y minus 1/4 is equal to negative root 3 over 2, the slope, times x minus pi over 6. So I'm using the point that they gave us, or that we found, the slope that we found, and then writing this in point slope form here. To find the approximation of f of 0.5, I'm going to plug in 0.5 for this. This is absolutely one I'd use a calculator for in order to do it. So my approximation is going to be y minus 1/4 is equal to negative root 3 over 2 times 0.5 minus pi over 6. If we do that, we're going to end up that y is about 0.270 if we use our calculator, and therefore f of 0.5 is about 0.270, rounding to 3 digits after the decimal place. So that is part A. Part B is much quicker because we are going to use our knowledge about concavity in order to figure this out. Since they said that this thing is concave up, so since f of x is concave up at x equals pi over 6, this is, what is it? Well, if we think about it, concave up, here's our concave up function, looks like a U. If we draw a tangent line, that tangent line is below it, so that means that this thing is an underestimate. This is an underestimate for f of 0.5. Nice. That is it for our review for this chapter. Again, I encourage you to go back and check out our old packets, try some of those practice problems, and feel free to stop by class or office hours if you have any questions. Have a great rest of your day, happy studying, and good luck on your chapter test.